layers encryption or with incremental encryption. I think it's time.
Okay.
Oh no. Okay, so good afternoon. I'm very pleased to introduce our speaker of today. Is Dr. Anish Chandran, who is a postdoc at Microsoft Research. And he's going to talk a very important topic, which is encryption for cloud. So this is really a timely topic. So
Thank you very much for the introduction. So the talk is going to be on some of the cryptographic challenges that we face in cloud computing and some solutions that we have to partially solve maybe some of these issues. And I must warn you that it's a talk that that is heavily biased towards my research interests and the kinds of problems that I've been working on. So when you think of a cryptographic protocol, traditionally this is what happens. Say you have parties, Alice, Bob, and other parties want to execute some cryptographic protocol. They communicate in order to do this, and sort of three properties that stand out would be invariably parties communicate directly with each other to execute this cryptographic task. So think, for example, you want to execute a credit card transaction over the internet with Amazon. You are encrypting your credit card information, sending it to Amazon, so you are interacting with Amazon. Amazon is maybe interacting with your credit card company and so on. So there's a lot of interaction between the parties going on. Secondly, parties do end up performing fairly computationally intensive tasks. So if it turns out that this encryption algorithm itself is very computationally intensive, it's still the parties who are doing the encryption algorithm locally on their system because they don't want to reveal their secrets outside of their system. And so parties are doing these computationally intensive tasks on their own, on their system. And thirdly, as I said before, parties store all their sensitive data on their own machines because they're scared to give it out somewhere else. Okay. With the advent of the cloud, what has changed? The cloud has brought about fascinating possibilities. Why would one need to use the cloud for anything? There are several reasons. The most important being the fact that now I want to access my secret data not just from one device, typically. Right? Today I have my iPad, I have an iPhone, I have my personal computer, and I want to be able to perform data that's related to my secret data from all these devices maybe at different times. And it's really a pain if I want to store all my sensitive data on all these devices or go around carrying my sensitive data wherever I need to. So it would be nice if I can just put it up somewhere on the cloud, and whenever I want to access my sensitive data, I can do so by talking to this cloud. Right? And also, the cloud provides a fascinating possibility that any computationally intensive task can be offloaded to the cloud. I don't need to. If I'm running a mobile device, then maybe I don't need to run any kind of expensive task on this device. Okay, and so now the world has sort of changed a little bit. Ideally, we'd like parties to communicate directly only with the cloud. It would be really, really nice if parties don't have to interact directly with each other. I'll have to wait for Amazon to be available at some particular time and talk to them. It would be really nice if I talk to the cloud only, and then I go away. I don't have to interact ever, and then another party comes, interacts only with the cloud, goes away. But still, we are sort of able to execute some cryptographic task without having to synchronize when we are getting together to run this task. And then, since the cloud is a powerful server, why not ensure that only the cloud performs computationally intensive tasks? And thirdly, the cloud is the one storing all the sensitive data on behalf of all the parties. Okay? So all this is great, except that now obtaining security in the presence of a cloud that we do not trust is a fundamental cryptographic challenge. So if we trust this cloud with all our secrets, everything is fine. It's very easy to execute whatever we want to, but if we don't trust this cloud, what happens? Right? And today I'll try and give you some issues that come up and how we can maybe solve some of them. Okay. The number one challenge that, as you might imagine, is we would like to store sensitive data on the cloud without the cloud learning anything about it. Okay? So in our picture over here, Alice wants to store sensitive data on the cloud, and the cloud should not learn anything about it. Uh, the obvious solution might probably work. Alice will, say, encrypt all her data with her public key, and store it on the cloud. And now, since the cloud sees only encrypted data, the cloud should not learn anything about it. Okay. This works fine, except that if we had any sort of access control on this on the data, now that needs to be sort of implemented on encrypted data. So think, for example, Alice wants to, say, give out her social security number to Bob alone because Bob wants to run some credit check or something like that. But she doesn't want Bob to learn all her secret information. She doesn't want Bob to learn her date of birth, her, I don't know, the other secret information that she has. So she wants Bob to learn only some portion of the sensitive data. So there is some access control that's defined over here. But now, since all this data is encrypted, this access control needs to be sort of implemented on encrypted data, which is a whole new challenge now that we face. And so if Bob comes to the cloud and says, give me the data that's meant for me, somehow the cloud must know what is the data that Bob is authorized to see and give only that data to Bob without learning anything. And so since everything is encrypted, the cloud sees garbage, how is it going to implement this access control? A third issue is reliability of data. Alice is now possibly storing all her secrets on the cloud, and maybe she doesn't even store a local copy of all her secrets. What happens if the cloud is unavailable? What happens if the cloud gets corrupted and data is no longer available? Is it lost completely? Typically, it would be nice if Alice uses, like, sort of multiple clouds, or the same cloud uses multiple servers to store the data in a distributed manner, so that any kind of corruption you can tolerate. Okay. So the outline of my talk is going to be as follows. As I said, it's biased by my research. There are three issues that I'll briefly talk about here. The first one is, how do you store sensitive data, such as health records, in the cloud, and still sort of manage an access control on this encrypted data. And for those of you who are interested, this is joint work with Chase and Vaikuntanathan. It appears at the Theory of Cryptography conference, and it will appear next month. Okay. The second question that I'll address is, how do you reliably store data on multiple clouds? Sometimes these clouds may not be connected properly. They may be connected by some poor degree network. So in this setting, how do we actually ensure reliability of data? This is a sequence of works with Carey and Ostrovsky. The first appears at iCal 2010. The second is very, very recent result. And the third is, how do we do biometric authentication of users? This biometric authentication of users has many applications even outside of the cloud world. It's a very user-friendly way to authenticate somebody, but there are several issues that appear over there. How can we do this? I'll briefly mention some results in that area. It's joint work with Karnakuthi, Ostrovsky, and Raisin. It appears in Stock 2010. Okay. So I'll first focus on the first part of this talk, that is how to store sensitive data like health records on the cloud and still manage an access control. Before that, any questions, feel free to stop me anytime if I'm not making sense. Okay, so the scenario is as follows. Alice has medical records that she wants to store on the cloud. Okay. Now the first question is, who is uploading this medical records? It could be any of the hospitals. She goes to the hospital, gets some tests done. The hospital collects all this data, and this hospital is going to upload Alice's medical records to the cloud. Okay, so the scenario is as follows. We have Alice's medical data that's uploaded by hospitals to the cloud. Okay? And then Alice has some access policy. What is this access policy? It's saying she has her favorite doctor to whom she wants to tell all her medical information, right? But then there's a nurse, and she wants the nurse to only learn any data that's marked scanned. So all these data are tagged in some way with specific keywords, and now she wants the nurse to be able to read only data that's marked scans. Okay? And thirdly, maybe Alice is taking part in some research study, and so she wants data that's explicitly marked for this research study to be available to the researcher, but the researcher should not get any other information. Okay? So this sort of governs some access policy that Alice might have. Okay? And this access policy is given to the cloud by Alice. So let's see how we can implement something like this. So the first solution would be, okay, send all Alice's data in the clear. Right? If that's the case, then the cloud can easily manage the access control. If the nurse comes and says, give me the data that's meant for me, cloud, of course, can look up this data and give it to the nurse. Right? Clearly, this solution is not good for us because cloud ends up learning, first of all, Alice's medical data completely, and secondly, in fact, it even learns the entire access policy. As we'll see later, the access policy itself might be sensitive in some applications. Okay. So second approach is, okay, let's have the hospitals encrypt Alice's medical data. So whenever data is uploaded, it's encrypted under Alice's public key and sent to the cloud. Okay. Now, this works in the sense that the cloud does not learn anything about the health records, but how do we implement the access policy? Because all this is encrypted data. Right? One option might be to say, okay, whenever a recipient wants data, involve Alice in the process. So if a nurse comes and says to the cloud, give me the data that's meant for me, the cloud will talk to Alice and say, hey, what is the data that nurse is allowed to see? And then Alice can do the appropriate action and give it to the nurse. This has several drawbacks. Number one, it requires Alice to be online whenever some recipient is coming for the data. Right? And secondly, Alice is actually doing the bulk of the work over here. So why make use of this cloud? This cloud is actually pointless. Right? Okay. So the ideal solution would be as follows. Alice is online only when setting up the policy. Okay. So she sets up the policy and says these people should get access to these portions of the data. And then she goes away. And she does not need to be available anytime afterwards. The hospitals upload Alice's medical data to the cloud. Somehow the cloud can manage this entire access control and send appropriate data to the appropriate recipients. So the cloud will be able to send all the data to the doctor such that the doctor can learn the contents of the data. She'll be able to somehow re-encrypt portions that are meant only for the nurse under the nurse's public key and send it to the nurse. Right? And she'll be able to re-encrypt data that's meant only for the researcher and send it to the researcher. And somehow the cloud will be able to do all these operations in some oblivious manner without learning anything about Alice's data or the access control. Okay, so this is what we are shooting for, and we'd like to get some solution which has this structure. Okay, so one potential approach one might think is the use of attribute-based encryption or a more advanced primitive predicate encryption. Predicate encryption essentially is the following tool. It allows an encryptor to encrypt data along with some tags, but these tags can be hidden, right? And it has the property that only those satisfying some access policy on this tag can decrypt the data, and nobody else can decrypt the data. Okay, so how can we maybe use predicate encryption to get some sort of a solution for our setting? So Alice picks a public key secret key pair for the predicate encryption scheme, sends the public key alone to the cloud. Now, whenever the hospital wants to encrypt data, they will use this public key to encrypt the data along with some specific tags. So each each record has some tag about what this record is saying. Now cloud stores encrypted data. Alice will do the following. Alice will give specific secret keys to each of the recipients. So she'll give the doctor a secret key skdoc, and this skdoc will allow decryption of all the data. Okay. She will give the nurse a secret key sknurse, and this sknurse will somehow magically allow the nurse to only decrypt portions that are meant for her, portions that have, for example, the tag scans. Okay. And the researcher similarly will receive a key skr that will allow decryption of data that's tagged research. Okay. And predicate encryption allows us to build such crypto systems. Okay. Now what can happen? The cloud can just give all the encrypted data to all these recipients, and the recipient can do the appropriate decryption and learn only the required portions of data. Right? So we would have ensured that only the right person ends up getting only the information that's meant for them. Okay. However, this type of solution has the following two drawbacks. Number one, it actually ends up revealing the access policy to recipients. Okay, the recipients end up learning everything. So that's the structure behind these predicate encryptions is such that the access policy is revealed. Why might this be a problem? Say Alice is taking part in some sort of research study that's related to like mental health or something like that, right? So now my access policy is going to say if the data is tagged mental research study or something, give it to the researcher, right? And now if the recipient is learning this access policy, this itself leaks information that, okay, there is maybe something wrong with Alice's mental health or something like that. And so that's why she has this, in fact, in the first place in the access policy. Right? So the access policy itself might be sensitive in some applications. And if we were to use this approach to solve the problem, we'd be revealing the access policy to recipients. Okay? Another drawback with predicate encryption based solutions is that actually in the recipients need to do work that's proportional to the access policy. So if you have a complicated access policy, then they need to do, in order to decrypt the data, they need to do something complicated as well. And this is something we'd like to somehow offload to the cloud. We have the cloud that's prepared to do expensive work for us. Somehow we'd like the recipients to just do normal decryption of simple ciphertexts and let the cloud do all the expensive work. And so if you were to use a predicate encryption based solution, we are falling short over there as well. So these are two issues that we'd like to address. Okay. So in this joint work that I was talking about, we actually present something that takes us towards this ideal solution. Okay. We introduce a new primitive that we call functional re-encryption. Okay. Functional re-encryption basically does the following. It takes some ciphertext of some message M along with some tag tau. Okay. Now it computes, it has some access policy F, and it computes F of tau, which will tell it some other public key, and it will re-encrypt the ciphertext under this public key. Okay. So it will take the ciphertext under message M, and it's going to re-encrypt it under some recipient public key. Whose public key does it re-encrypt it under? That depends on the access policy. Okay, so that's what the functional re-encryption primitive does.
Excuse me, but
Yes.
then, how does it differ with respect to proxy re-encryption schemes which you combine with identity or attribute-based encryption?
Great question. So proxy re-encryption schemes, yes, they don't have inherently in them, they don't have an access policy in them.
But you can combine with identity-based encryption so that,
Identity-based encryption is not going to give you an access policy. Possibly you can use attribute-based encryption.
Exactly. So, yeah. That's my question.
To the best of my knowledge, they cannot, known schemes are such that you cannot combine them.
I have seen recently, because I was looking for proxy re-encryption to see whether you can combine with attribute-based encryption. Because that's exactly what you want
Sure.
to do as well.
There's one more problem.
Yeah.
Attribute based encryption does not actually hide the access policy. And it does not hide the tags also. So tags are public in attribute-based encryption. Access policy is public in attribute-based encryption.
I'll check with those schemes.
So any
see
kind
what
of
they do.
those schemes are going to reveal more information than what we want. So we want a solution where the cloud actually learns nothing. It's just sort of doing this in a completely oblivious.
The cloud in your scheme knows the access patterns.
No,
So it doesn't know the frequency of the queries.
no, nothing.
So are you using shuffling? No, the pattern of queries, how frequently the data is accessed.
So by the recipients who
Yeah.
access and whether they're accessing the same data again.
Yeah.
So that's not something I'll be covering today, but that can be
But this
handled
scheme,
using.
doesn't hide this.
This scheme by definition doesn't hide it,
Okay, good.
but
That can be
but that's not a
done.
property that we're looking
Yes.
at focusing at right now. You can get that separately on top of it.
Since you said the cloud learns nothing, nothing has to be defined.
Yeah. So
Thank
we
you.
can take care of that separately. I'll
Yeah.
not be speaking about that
Yeah.
today. Okay. So how can we make use of this functional re-encryption primitive? So here's what we do. We have the recipients, the doctor, nurse, and researcher, who have their own public key, secret key pairs. Now, the advantage of functional re-encryption is that we don't need to give them any specific kind of keys or anything. They have their own public key, secret key pairs, and we're going to make use of them. Okay. Now, Alice is going to take her public key. She's also going to have a public key, secret key pair, and she's going to compute what we call a re-encryption key, RKF. Now, this re-encryption key depends on the access policy that Alice has. Okay. Now Alice goes away. She doesn't need to be involved in the process anymore. Okay. Now when hospitals encrypt the data, they're going to make use of the functional re-encryption algorithm to encrypt data along with some tags. And they're going to send this to the cloud. The cloud is going to do the following in some oblivious manner without learning anything. It's going to compute f of tau, and then it will re-encrypt the data under the public key determined by f of tau. Okay, and it will store this data or send it to whoever needs it, and the appropriate recipients can try and decrypt this data. If they are successful, that data is meant for them. Okay. Let's see an example. Suppose we were encrypting data with some tag cardio, right? And Alice wanted that only the doctor should be able to read this data and no one else. Okay? Then what will the cloud do? Somehow, in an oblivious manner, the cloud will compute f of cardio, which will result in doctor. And the cloud will re-encrypt this data under the doctor's public key. So what comes out is an encryption of the data under PKD, which is the doctor's public key. And so now only the doctor will be able to decrypt this data. Okay. And somehow we'll ensure that all this happens without the cloud learning anything about the message or about the access control. Okay. So if these recipients were to see this data, the doctor can decrypt it and he will get the data. The nurse is going to just see garbage, and so they learn nothing. Okay. So a couple of advantages of our solution is that the access policy is hidden from the cloud and the recipients. And note that recipients are decrypting only regular ciphertexts over here. Since the recipients had a public key secret key pair and which they normally used for encryption operations, and they were decrypting only that kind of those kind of ciphertexts, there was nothing dependent on Alice's access policy. So all the heavy work is done by the cloud. Okay. And thirdly, in fact, it turns out that it can be the case that recipients are even unaware of access control. So if they go to the cloud and say, give me the data that's meant for me, they'll get the data that's meant for them. They don't know what happened, whether this data went through access control or anything like that. They don't even know that they might not be privileged to see some information. Something like that. Okay. Some other advantages of functional re-encryption are the following. Number one, revocation of keys is fairly easy if we trust the cloud. So suppose I decide that today I don't want to give the nurse access anymore to any more data that she has not seen. All I need to do is go to the cloud and say, here is a new re-encryption key based on a new access policy F. Please use this henceforth. And if we trust the cloud to erase the previous re-encryption key and use the new re-encryption key, then revocation is easy. We do not even need to involve Alice in this process. Nothing needs to be done. Okay. It turns out that our solution can even handle collusion between recipients and the cloud. So for example, say the nurse is somehow able to collude with the cloud. Maybe now the nurse is trying to find out information about my secret key, my data, more than she can already see. We ensure that's not possible. And finally, a small advantage is that recipients need not be even involved in the setup phase. If you notice the setup phase, all it required was Alice to send some re-encryption key to the cloud that depended only on the recipient's public keys and her secret key and access policy. So she didn't need to talk to the recipients more than just looking up their public keys. Okay. So what I'll do is I'll very briefly spell out some of the techniques used to obtain functional re-encryption. This is going to be at a very high level, but hopefully it will convey some ideas. So starting point for the solution is what is known as regular re-encryption, which has received a lot of attention. Regular re-encryption is the following gadget. It has two parties, Alice and Bob, and it allows one to do the following. Alice can upload some re-encryption key to the cloud such that whenever the cloud receives data that's encrypted under Alice's public key, it can transform it into ciphertext that's encrypted under Bob's public key. And it can do this without learning anything. What is without learning anything? It has to be formally defined. I'll not get into all that over here. But one can show that all this can be done in such a way that cloud can just do this operation without learning anything whatsoever. Okay? And let us look at the re-encryption scheme from the work of Hohenberger et al. From 2007. At a very high level, again over here, the scheme looks as follows. This is not exactly how it looks, but hopefully this will be enough to convey some ideas behind the scheme. So the public key comprises of an element G to the A, where G is a generator of some prime order group and A is an exponent, and the secret key is the value A. Similarly, Bob's public key and secret key are G to the B and B. Now, the re-encryption key that is sent to the cloud roughly looks as follows. It's just Alice takes Bob's public key, PKB, and raises it to 1 over A. Okay? And now when the cloud gets an encryption of message M under Alice's public key, which is G to the A, it can translate it into an encryption of the same message M under Bob's public key, G to the B, making use of the re-encryption key, RKAB. Okay? I'm not getting into any details over here, but the bottom line is that re-encrypting from a public key G to the A to the key G to the B can be done with the help of a re-encryption key G to the B over A. If you look at what PKB to the 1 over A is, it's simply G to the B over A. Okay? There's more going on over here, but this is sort of the bottom line from their scheme that we can use. Okay. So let's look at a high-level idea for constructing a functional re-encryption scheme. For now, let's consider only two recipients. Okay. Now, Alice's public key is going to be not just one group element, but a vector of group elements, and the corresponding exponents are all going to be secret keys as well. Okay. Now, what we're going to do is, when we want to encrypt a message M with some tag I, we're going to use key G to the AI from the public key. Okay? And now let's again assume a very, very simple access policy. I'm not getting into more details here. Let's assume the access policy is simply f of 0 equal to 0, f of 1 equal to 1, meaning if the incoming ciphertext was tagged with tag 0, I want the first recipient to be able to, or 0th recipient to be able to read the data. If it's tagged with tag 1, then I want the first recipient to be able to learn the data. So it's a simple access policy that we want to implement. Now let the recipient's public keys and secret key pairs be defined as follows. It's just G to the B0 and B0 and G to the B1 and B1. Okay, just like how you would imagine it from the previous key. Okay. Now, one key idea is, say we could do the following. If we could find a single re-encryption key G to the alpha that will do both the operations, that is, it will re-encrypt from G to the A0 to G to the B0, as well as G to the A1 to G to the B1. Okay? Then I claim that this will solve at least one problem that we have. Namely, it will hide the function f. Why is that the case? Note that if incoming ciphertext was encrypted with tag 0, then it's encrypted under G to the A0. Okay? Now, the cloud, irrespective of what the ciphertext is encrypted under, is going to use a re-encryption key G to the alpha and perform some operation, and out is going to come encryption of the same message under G to the B0 if the incoming ciphertext were tagged with 0. If it were tagged with 1, out comes ciphertext encrypted with G to the B1. Okay? And it's important here that if it's a single re-encryption key that's doing the operation, then no matter what the incoming tag is, the operation done by the cloud is exactly the same. There's no branches. He never checks anything. Nothing is going on here. Okay? So he runs the same operation. Out comes the right ciphertext. There's much more details going on over here, but this is just like sort of one component in this construction. Okay, so the re-encryption key is simply G to the alpha that's given by Alice to the cloud. Okay, and out comes an encryption under the appropriate public key of the messaging. Okay, a significant amount of work needs to be done in order to make this scheme secure. The scheme, as I presented it over here, is not secure, but this is sort of one idea that goes into constructing these kind of systems. Okay? Okay, so now that we have functional re-encryption, the natural question is, can we do everything with functional re-encryption? It seems like something nice to have. Is it the answer to all our problems? Unfortunately, no. Number one, the access policy. Can we obtain solutions for arbitrary access policies? It turns out no, we cannot do that. Our solution is for a small class of access policies. In fact, we show that arbitrary access policies are impossible. One cannot construct functional re-encryption scheme for arbitrary access policies. How do you show that? You show that by constructing an access policy for which one cannot hope to obtain a functional re-encryption scheme. This builds upon some known impossibility results in the area of program obfuscation. There are several questions though. One question we can ask is, can we obtain smaller ciphertexts? In our solutions, the ciphertexts are somewhat large. Can we obtain solutions with smaller ciphertext size? We have some very recent results showing that, yeah, we can indeed obtain smaller ciphertext size. We're willing to make some other assumptions. And actually, there are many interesting open questions in this line of work. I'd be happy to talk to you offline about this. So now that we're done with the first part, I'd like to pause here. Anybody has any questions on the first area? Because the second one is sort of in a different um, line of work. So if you have any questions in this first area, I'll be happy to.
I have a couple of questions, but take them out offline.
Sure, sure.
Questions?
Okay. So the second part of my talk deals with reliable storage on multiple clouds that are connected by sparse networks. So here's the setting. Alice wants to store all her files in the cloud. But of course she wonders, will the cloud store my data reliably? Like, what happens if something is lost? And a natural question is, maybe if she uses multiple clouds, or if the cloud uses multiple servers to store her data, there'll be more reliability. So the setting is something as follows. There are multiple clouds. Alice's file is there, F. What she does is she encodes her file using some error correcting code so that it can be recovered later on. And let the error correcting code give out components v1 through vn, and she's going to give all these shares to different servers. Okay, so server 1 is going to store v1 for her, and so on and so forth. Okay, and this is done to ensure reliability. Now, it may turn out that some of these servers may become corrupted, their files may become damaged, a lot of things could happen. And the clouds wish to ensure correctness of Alice's data, even when some of these clouds may be malicious or files may become corrupt. And they do not want to involve Alice every time in the process to ensure that whatever copy of Alice's file they have has been stored reliably. Okay? And so typically what happens is we need to ensure that clouds can run some joint computation on shares. So if we go back to our previous question, if now the cloud is not a single entity but multiple entities, in order to provide the functionality, we need these servers to talk to each other and run some arbitrary computation, because now they do not have the data wholly, they have only some parts of or some shares of this data. Okay, so the need is for the clouds to run some joint computation on these shares of data. What computation they need to run, I won't have time to get into that today, but a fundamental building block in some of these protocols is that of Byzantine agreement. Okay, so I'll mention some problems in this area and solutions for that. Byzantine agreement is a classical problem introduced in the 80s. It's the following notion. We have n players who want to run a protocol. Party Pi has some input Vi. Okay? Now, we want the protocol to satisfy two properties. Number one, agreement. That is, all honest nodes must output the same value at the end of the protocol. Okay? The second condition is that if all honest nodes actually began the protocol with the same value, then they will indeed output this value at the end of the protocol. And the second property is what actually makes the problem non-trivial. Okay. And Byzantine agreement has many applications in distributed computing and in secure computation, data consistency, and it's actually a fundamental building block in secure computation, which is very important in cryptography. Actually, several protocols exist for this task, and a lot of them have considered communication complexity, round complexity, computational complexity of parties, and so on and so forth. So a lot of work has been done in the area of Byzantine agreement, but most of them make an assumption that every two parties in this network actually share a reliable channel. That is, they have a physical channel through which they can actually communicate reliably. Okay. And this might not always be the case. You might be connected by a poor degree network, yet you may want to run a Byzantine agreement protocol. Okay. So now, in light of this, Dwork et al. Introduced the beautiful notion of almost everywhere agreement. So it's the same setting as before, except that now parties are connected by some communication network G. Okay. and only nodes that share an edge in G share a reliable channel. There's some sparse network by which they are connected. And note that in this setting, one cannot actually obtain agreement amongst all honest nodes. Why is that the case? Say an honest node is connected only to malicious nodes. Then there's no way we can even communicate reliably with this honest node, let alone running some computation with the help of this honest node. So in some sense, this honest node is doomed, right? We cannot help it in any way. So there actually ends up being a classification of nodes in this setting. In my picture over here, red nodes are adversarial nodes in this network. We don't know which are the adversarial nodes, but there are some adversarial nodes in the network. The green nodes are honest nodes for which we'll guarantee that they will reach agreement. And these nodes are known as privileged nodes. Okay? And then we may have some black nodes in the network. These are honest nodes for which we don't know because of their poor connectivity. They are in a bad neighborhood. We don't know whether they'll reach agreement or not. We may not be able to ensure that they reach agreement. Okay. So the goal is fairly clear over here in this setting. We want to minimize the degree of the graph. So as sparse a network as possible, we want to construct on which we can have Byzantine agreement protocols. We want to tolerate as many corruptions as possible. A constant fraction is the best, but can we tolerate as long as, say, 20% of all the nodes are corrupted? Even then, can we ensure something? We want to, of course, minimize the number of doomed nodes. We don't want to give up too many honest nodes. Right? And of course, the running time of the algorithm is also important here. So let me just give a sampling of some of the results in this area. Dweck et al. In the original paper constructed graphs of constant degree, okay, and the number of corrupted nodes that they could tolerate was roughly n over log n. In the same paper, they construct graphs of degree n to the epsilon for some constant epsilon. Okay, so the degree is really, really high. But the number of corrupted nodes that they can tolerate is actually the best, so constant fraction. Okay. Then, in a very surprising result, Upfal, in a beautiful paper, he showed that you can construct graphs of constant degree, and the number of corrupted nodes tolerated can be constant fraction as well, so it's sort of the best possible. Unfortunately, the running time of the protocol in Upfal is exponential in the number of nodes in the network. Okay. So the question was, can we obtain agreement protocols on graphs of degree much less than n to the epsilon, tolerating a constant fraction of corruptions? Okay. So in recent work with Garay and Ostrovsky, we show graphs of polylogarithmic degree, so we reduce the degree significantly. The number of corrupted nodes is the best possible constant fraction. And in fact, we even succeed in reducing the number of doomed nodes. The number of doomed nodes is t over log n. So it's reduced as opposed to the earlier cases where it was t. The running time of our algorithm is now polynomial. Okay. So let me briefly outline some of the steps needed to obtain almost everywhere agreement. The steps will be as follows. First, we'll construct a specific graph G that has small degree. Then what we'll do is we'll focus on constructing what is called a reliable message transmission scheme between any two honest nodes. Okay, that is, we first want to ensure that if there are two honest nodes that are not connected by a reliable channel, how can they communicate reliably? That is, they want to send messages through adversarial nodes in the network and yet communicate reliably. So that will be the focus of most of these protocols. Once we are done with that, then we can use standard techniques to run any agreement protocol and obtain our results. So the focus will be on sort of the first two steps. I may not have too much time to talk about this, so I'll just quickly mention how you construct the specific graph. The way is to sort of place them in sort of overlapping partitions and then connect them in some specific way. Some of the tools needed are from the theory of expander graphs and so on. So you need sort of the property of expansion helps, but it's not necessarily sufficient. You need to put in graphs in some specific manner, and once you connect them, you can show that they can reliably talk to each other. I don't think I'll have time to go over this, so I'm just going to state the result over here. Okay, so the main theorem that we can show is we can construct graphs of polylogarithmic degree, right? And adversarial nodes are these red nodes. They can be arbitrarily chosen by the adversary, as long as just there's some bound on the number of nodes that corrupts. The corruptions can be made adaptively at any time, even during the protocol, and so on and so forth. The number of privileged nodes is actually almost everybody. So we can n minus like t minus t over log n as the number of privileged nodes that we can ensure can reach agreement. And we can ensure that they can communicate reliably. Once they can communicate reliably, they can reach agreement. Okay. Once we are done with that, one naturally wonders, is there anything that the adversary can do beyond just corrupting nodes? And in fact, he can. What could he do? He could actually disrupt communication between honest parties as well. Right? So there are two honest parties, maybe their communication link, something bad happens. Right? So in that setting, what can we do? We can model it by considering the so-called edge corruption model, where we additionally allow adversary to corrupt edges in the network. And so in this setting as well, we have some results on low degree networks where we can reach agreement. Okay. So there are many open questions in this area. Can we obtain agreement protocols on constant degree graphs tolerating constant fraction of node corruptions? This is not something that's known. Agreement protocols on polylogarithmic degree graphs tolerating constant fraction of node and edge corruptions. This is not known. What we get is graphs of degree n to the epsilon, so there's a gap over there, it can be closed maybe. And maybe we can obtain better agreement protocols for specific graphs that model existing network structures better. We can maybe look at network topology and see if there are some particular graphs that get the results. So I'm going to wrap up by just stating some results in the area of biometric authentication of users. The setting is as follows. So again, this is applicable in many situations, but I'm just using the cloud as an example. Say Alice goes to the cloud to perform some cryptographic task. The cloud is going to tell Alice, please authenticate yourself to me. I need to know that it is indeed you. Right? And Alice wants to use an easy to reproduce key. Right? If it's some random looking string, then she has to store it somewhere or remember this. It would be nice if it's a password or something like that. The problem with passwords is they are typically very short. They don't have enough randomness or entropy, as what we would call it in them. And so passwords are not typically that useful. But what can be used is biometric data. If I can scan my fingerprint, I can take an iris scan, or I can give responses to some passphrases. These all have a good amount of entropy in them. They have unpredictability, but the drawback is that they are not uniformly random. That is, if you take a string of length n, it's not the case that all strings will appear with probability 2 to the minus n, right? Which is sort of a basic requirement for any cryptographic task, and is assumed by almost every cryptographic task, right? And so what would be nice is if Alice and the cloud can run some key agreement protocol to take this biometric data and convert it into a uniformly random key. Then they can use their favorite crypto primitive, right? So the question is, how do you translate data that only has some entropy into a uniformly random string? Okay? And the goal over here is you want to extract as long a key as possible from the biometric data, because randomness or unpredictability is at a premium over here. So if it turns out that our data has 100 bits of unpredictability, meaning that adversary can guess it with probability 2 to the minus 100 at best, then we want to get out a key that's 100 bits long, that's uniformly random, so that even that key, the best he can do is guess it with probability 2 to the minus 100. It will be pointless if from starting with this high entropic data, we extract like a key that's 10 bits long, then adversary can easily guess it. Right? And so, sort of minimizing unpredictability loss has been a big focus of this work. And so, the main result in the stock 2010 paper is we give a protocol that extracts an optimal length key k from the biometric data, and this happens even in the presence of malicious adversary. We can extract as long a key as possible. So if you start off with 100 bits of unpredictability, then we can actually extract a key like almost all of it. We can get almost 100 bits random key from this. And this sort of makes use of techniques from error correcting codes, randomness extraction. I'll be happy to talk about it if you're interested. Okay, so with that, I'll actually conclude by saying that the cloud provides us actually with new possibilities. We can store data in one single place. We can offload all our computation. But while it gives us a powerful model of computation, this cloud is a very, very powerful entity, and we need to protect our data in the event that this cloud is not trusted. And so several fundamental cryptographic challenges are there in this line of work. There have been techniques to solve some of these. There have been recent theoretical breakthroughs like notion of fully homomorphic encryption and so on. They've helped significantly in solving some of these problems, but not all problems have been solved yet. In particular, some problems related to the notion of controlled decryption is not particularly addressed by fully homomorphic encryption. And so there are very interesting questions in that line of work. There are plenty of interesting open questions. One question that comes to mind is, can we outsource arbitrary multi-party computation securely to the cloud? So, for example, say I have some input x1 and you have an input x2, and we want to compute some joint function on this. We want to compute f of x1, x2. Think, for example, two hospitals who want to compute some joint statistics on their patient database, but they do not want to reveal their respective patient databases to one another. Right? Now, can they somehow outsource this entire computation to the cloud and let the cloud compute it for them and give back just the response, so that they don't have to do any of the work, right? And that's received some attention the last 2-3 years. The main challenge over there is, if the cloud lies about the response, the cloud lies about statistics, can we catch such a cloud and ensure that whatever response is given back by the cloud is actually correct, right? And so one way to do that will be, of course, to execute the protocol our own selves and see what happens, but that's pointless. We don't want to do that. And so can we somehow efficiently, just cheaply verify that the computation was correct without having to do the computation by ourselves? So that's another line of work that's received attention last couple of years. And yeah, thank you. Any questions?
Okay, thanks.
I guess some file servers have administrators for auditing reasons. How would your protocol prevent them from accessing the data that's been uploaded and not encrypted yet?
Sure. So by cloud over here, we do mean even administrators who have access to whatever is stored on the cloud. Since all data is encrypted under recipients' public keys and users' public keys, these admins don't have access to these keys. And so any data that's stored on the cloud, even if they can read the data, it's all just garbage to them because it's just ciphertext encrypted data.
have perhaps a practical question because every time because we have been working also on encrypting this data on the cloud, but the practical problem we see is the following: at the end, a user will download a big bunch of data, even though the user can only decrypt a small portions
Yes.
of the data.
Yes.
And when the cloud charges you for this, so how do you prevent that?
So-
That's a practical.
Yes, indeed. So it is. I don't think it is possible if we want to hide the access policy also. But if we don't want to hide the access policy, we have some solutions where the cloud can obtain encrypted data that's meant for some particular user, and the cloud knows which user can decrypt this data.
We really.
And so it can read
yeah.
only that particular data,
Yeah,
not
we were
more.
thinking, about something which is a little bit different,
Uh-huh.
which really you split the data in some certain containers,
Mhm.
and the user have to prove that somehow they can download those containers. By use a different approach, which is really not dependent on the access control.
So that would
policy.
still
Then you
require
get,
the
yeah.
cloud to place the appropriate data in the appropriate
But if you
bin.
look, the Azure really has these operations like put or the Amazon cloud as this basic where you say put this data into this container. They have really already this type of
Right, so the cloud is going to learn where it's putting the data, right?
But it has to do. Otherwise, how do you use a cloud?
Yeah, so it will learn some portion of the access
Yeah.
policy. That's what I was saying. So if you're willing to sacrifice
Yeah.
giving up the access policy, then it can be done.
But that will be a problem
If you-
because in the case of an organization which has 1,000 users sharing the data,
Yeah, I agree.
there's going to be a problem.
I agree. If you want to hide the access policy, this is a fundamental problem. I don't immediately see a way out.
One
Maybe there
could
is
come,
something,
but has to do some kind of randomization type of access. It's downloading some data which are really the user can access, others which the user cannot do. You make that in such a way that the cloud doesn't learn any meaningful patterns at the price of downloading a little bit more data, but not downloading
it's possible.
everything.
It's possible that you can do
Okay.
something like that.
But so, you have a question?
Brief one. So you said functional re-encryption cannot handle all kinds of access policies. So are there a particular class of, could you maybe throw a little bit more light on, is there something specific about the types of access policies that functional re-encryption can handle, or is it sort of too
So
complex?
it can handle, as long as the input and output, the domain and the range of the function is not too big, it can handle arbitrary functions. So once it starts becoming a little big, things get messy. So it's a little.
But
that's
just because I
basic.
also had a similar questions. But so can you, for example, say that these two users can access the same piece of data?
Yeah.
Yeah,
We can,
okay.
We can do it.
Even though they have different, of course, public key.
That's fine.
Okay.
That's fine. So it would require more work in the access policy side. You need to upload something more, but this can
Yeah.
be done.
Okay. Yeah. Okay. I think are there other questions? Again, thanks for this very.